Every time your refrigerator kicks on, you hear a low, vibrating hum. It's a sound we've lived with for over a century, the signature of a mechanical beast hidden inside our kitchen appliances. That hum is the sound of a compressor, a physical pump pushing chemical refrigerants through miles of metal tubing. It's a brilliant piece of engineering, but it's fundamentally a brute force solution to a thermodynamic problem. But a massive shift is coming. According to the latest IEA reports, we are finally moving away from these mechanical giants towards something far more elegant: solid-state cooling.
To understand where we're going, we have to look at the limits of where we are. Traditional vapor compression relies on the expansion and contraction of gases, which requires moving parts, seals, and fluids. These systems are incredibly reliable, but they've hit a ceiling. They are noisy, they use chemicals that can impact the environment, and they are difficult to miniaturize beyond a certain point. The engineering challenge of the decade has been to find a way to pump heat without moving a single part, and the answer lies in a strange physical phenomenon called the caloric effect.
Imagine a material that gets cold not because you put it in a freezer, but simply because you changed the magnetic or electric field around it. This isn't science fiction, it's material science. The 2026 IEA report highlights this as the solid-state pivot. It's the moment where specialized ceramics and alloys replace the noisy compressors of the 20th century. But how does a solid piece of ceramic actually pump heat? To find out, we have to zoom in, past the surface and into the very alignment of atoms. Think of it like a crowd of people in a room. Normally, everyone is moving in different directions. That's high entropy, which we perceive as heat. But if a drill sergeant walks in and tells everyone to stand in perfect rows, the chaos disappears. In the world of atoms, this sudden ordering releases energy as heat. When the drill sergeant leaves and the crowd scatters again, they absorb energy from their surroundings to get moving. That absorption is what creates the cooling effect. This is the core of the caloric effect. By using magnetic or electric fields to order and disorder the atoms in a solid material, we can create a cooling cycle without a single drop of liquid refrigerant. The engineering is brilliant because it's silent, it's incredibly compact, and it could potentially be much more efficient than the systems we use today. But the real genius is in the materials themselves, the specialized alloys and ceramics that make this atomic dance possible. Let's look at the chemistry of the chill. There are two main ways to trigger this effect. The first is the magnetocaloric effect, which uses powerful magnetic fields to manipulate the spins of atoms in metals like gadolinium. The second is the electrocaloric effect. Instead of magnets, it uses electric fields to polarize specialized ceramics. This is particularly exciting because electric fields are much easier to generate in small devices. Both methods achieve the same goal. They force the material into a low entropy state, causing it to dump its heat into a heat sink and then absorb heat when the field is removed. The secret sauce is in materials like gadolinium silicon germanium alloys. These are giant magnetocaloric materials that undergo a massive temperature change with even a modest field. When the magnetic field hits these alloys, their internal structure literally shifts. It's like a microscopic phase change, similar to water turning to ice, but happening entirely within a solid metal. This phase change allows the material to move a significant amount of thermal energy. But there's a catch. A single pulse only changes the temperature by a few degrees. To get a refrigerator down to 4 degrees Celsius or a freezer to -18, engineers have to use a clever trick called active magnetic regenerative cooling, or AMR. Think of it like a bucket brigade. Each stage of the material gets slightly colder than the one before it, stacking the cooling effect until you reach the desired temperature. This stacking process is how we overcome the temperature lift limitation. By cascading these solid-state pulses, we can create a powerful, continuous cooling stream. In electrocaloric systems, the process is even more direct. We use thin film ceramics, often just micrometers thick, which can be layered like a deck of cards to increase the surface area. These layers can be switched on and off thousands of times per second. This high-frequency operation allows a very small amount of material to move a surprising amount of heat. Because there are no heavy compressors or bulky coils, these systems can be integrated directly into electronics, cooling the very chips that generate the heat. But it's not just about the materials, it's about the engineering trade-offs. While solid-state systems are silent and compact, they face a major challenge: the temperature lift versus efficiency curve. Traditional compressors are great at creating a huge temperature difference, like 40 degrees, very quickly. Solid-state systems have to work harder to achieve that same lift while remaining efficient. However, for smaller temperature differences or for applications where space and noise are the priority, solid-state is the clear winner, and that's where the future gets really interesting. The most immediate impact of this technology isn't in your kitchen, it's in your pocket. As our devices get more powerful, they generate more heat than traditional copper pipes can handle. Solid-state cooling allows for microscale thermal management. We can cool specific hotspots on a chip with surgical precision, something a fan or a liquid loop could never do. This means faster processors, longer battery life, and devices that never feel hot to the touch. It's the hidden upgrade that makes the next generation of AI hardware possible. But let's think bigger, or rather, let's think about what we wear. One of the most ambitious applications for electrocaloric cooling is personal climate control, integrated directly into clothing. Because these materials are solid and can be made flexible, researchers are developing cooling textiles that can lower your body temperature by several degrees using just a small battery. Imagine a world where outdoor work in extreme heat is safe, or where we can lower the AC in our homes because our clothes are doing the work for us. That's a massive energy saving. The 2026 IEA report suggests that solid-state cooling could reduce global energy consumption for space cooling by up to 15% by the middle of the century. By removing the need for greenhouse gas refrigerants and replacing inefficient pumps with solid-state materials, we're not just making things colder, we're making the planet's future brighter. The transition won't happen overnight. We still need to bring down the cost of materials like gadolinium and perfect the manufacturing of large-scale ceramic stacks. But the engineering path is clear. We are moving from the age of moving parts to the age of moving fields. It's a shift from mechanical brute force to quantum-level elegance. And while the physics might be complex, the result is simple: a world that is quieter, more efficient, and perfectly chilled. Next time you hear that old refrigerator hum, remember, it's the sound of a dying era. The future of cooling is silent, it's solid, and it's already on its way. We've spent a century mastering the expansion of gases. Now, we're learning to master the alignment of atoms. The caloric effect is more than just a cool trick. It's a fundamental shift in how we interact with the thermal world. From the chips in our pockets to the clothes on our backs, the hum is fading, the chill is becoming solid, and the engineering behind it is absolutely brilliant.